primitive sorting methods like bubble and insertion sort work fine on a handful of items, but as data scales up, they hit a brutal mathematical wall. Their performance is quadratic, meaning they eventually choke on the sheer volume of comparisons. Algorithm number 4 on our list completely shatters that ceiling: merge sort. How do you build a mechanism that runs at the exact same speed, whether the initial data is completely randomized, perfectly ordered, or entirely backwards? Severing the connection between the data's starting condition and its processing time allows distributed systems to handle billions of records without the risk of an exponential slowdown. In 1945, John von Neumann was finalizing the design for the EDVAC. His work established the stored program architecture, the idea that a computer keeps its active instructions in the exact same memory as its data. To prove this theoretical machine could actually process information, he needed a concrete test case. He drafted a 23-page handwritten proof of concept. That document was the first recorded execution of merge sort. The basic hardware architecture of the device you are watching this on, and the logic required to efficiently sort its data, were drawn up by the exact same person at the exact same time. Merge sort relies on a strategy called divide and conquer. It recursively splits an unsorted list into halves until each piece is completely isolated, and then meticulously stitches them back together. This diagram maps out the split phase. At the top, we have an unsorted array of numbers. The algorithm slices it down the middle, creating 2 smaller lists. It continues this halving process down the tree until every single number sits in its own separate list. Mathematically speaking, an array containing only one item is, by definition, already sorted. Now the algorithm works its way back up. It pairs off those individual numbers, merging them into lists of 2, then 4, building progressively larger, sorted sequences. This graphic shows the exact mechanics of the merge step. We have 2 sublists, left and right, and both are pre-sorted. The algorithm places a pointer at the front of each. It compares those 2 front elements, grabs the smaller one, and shifts that pointer forward. Because both inputs are already ordered, the entire merge happens in one smooth, linear pass. You never evaluate elements across the entire massive dataset at once. By only comparing and combining short, pre-ordered lists, the algorithm neatly steps the exponential cost of an unsorted pile. This division method provides an ironclad mathematical guarantee. The best, average, and worst-case time complexities of merge sort are all strictly O of n log n. This chart visualizes why that math works. Having the list repeatedly creates log n levels of depth on the vertical axis. And across every single level, merging the pieces back together requires touching all n elements exactly once on the horizontal. The initial splitting phase does not check the values of the numbers. It simply cuts the lists in half. That blind, mechanical division ensures the algorithm's performance will never degrade. When we look at the modern Python implementation, we can clearly see this structure. The function divides the elements and then triggers itself recursively to handle the newly created left and right halves. The critical decision happens down in the merge loop. The code asks if the left element is strictly less than the right element. If there's a tie, the left side always wins. This choice preserves the original order of duplicate items, ensuring algorithmic stability. There is a physical cost to this efficiency. Because you cannot cleanly merge 2 sorted lists within their original footprint, merge sort requires a separate temporary memory buffer the exact size of the input data. It deliberately sacrifices a linear amount of RAM space to buy absolute certainty in processing time. That trade-off makes it the backbone of big data. When you have terabytes of database records, they are too massive to fit into a system's random access memory. You have to rely on a process called external sorting. The computer pulls small, manageable chunks of data, sorts them, and writes those organized blocks back to the hard drive. Then it uses the merge phase to sequentially stream those blocks into one cohesive file. And because the algorithm is stable, database architects can sort records by an initial key, like a name, and then by a secondary key, like a date, without scrambling the original alphabetical order. Physical hard drives are incredibly fast at reading data sequentially, but terrible at jumping around randomly. By streaming sorted runs in straight lines, merge sort operates in total harmony with the physical hardware. In 2002, a developer named Tim Peters optimized this process even further, building a hybrid of merge sort and insertion sort known as TimSort. It identifies small, already sorted chunks within the data and stitches them together using the merge logic. Today, TimSort is the default sorting algorithm, quietly running under the hood of Python and Java. 8 decades after the end of the Second World War, every time you call a standard sort function in modern software, your computer is executing the exact logic John von Neumann mapped out with pen and paper. You can explore the full Python implementation of this algorithm in Imran Ahmed's book, 50 Algorithms Every Programmer Should Know. Merge sort proves the power of meticulous division. But what happens if you allow unsorted elements to jump across massive gaps in the data before settling down? We'll see that in algorithm number 5, shell sort.